Hey there, this video is going to just briefly go over some things regarding exponential functions and their graphs. What we've done up till now have been polynomial functions, and those are algebraic functions, but exponential functions and logarithmic functions are non-algebraic. They're called transcendental functions. So here's what they're going to look like. They're going to look like f of x equals some number to the x. The difference here is my variable is in the exponent now. That's not something that we've done up to this point. Now I also need to say that my base is not 1, because if I had y equals 1 to the x, well, 1 to any power is just 1, so that ends up just being a horizontal line, which is a constant function. Okay, let's remember that when we take f at 4, and 4 is an exponent, an exponential expression is written 2 to the 4th, and that's 16. 2 multiplied 4 times. If it is a negative number that turns out to be your exponent, make sure you kick it downstairs. That becomes a positive exponent, and then compute your number. If you have a fraction, we know how to deal with 2 to the 5/3. The number that's on the bottom becomes your index. The number that's on your top is your exponent. You can do this on your calculator because you have a cubed root button in your math menu. The easiest way to do exponents that are fractions are to use a caret and then make sure that you put your exponential fraction in parentheses. If you have a radical like this, I would do the same thing. Remember, this is your exponent. So 2 to the radical 3 would be best done with the caret. When you look at the graph of exponential functions, there are a few things that you will notice. These have different bases, but notice that they all rise from left to right, and they all go through the point 0, 1. In fact, any base raised to the 0 power would be 1, except for 0. So 7 to the 0, 4 to the 0, 2 to the 0, it all is 1. So they all go through this point. You'll also notice that I can put any number I want in here for x, so the domain is all real numbers, but the range, what comes out, is going to be a positive number. I don't have any values down here. So not only do they rise from left to right, go through the point 0, 1, they're continuous, and then I can also take a look at how the base affects the steepness. So take a look at the bases of these three equations. I've got a 7, a 4, and a 2. And if you look at the graph, the larger the base, the steeper the graph. Now notice what happens when you put a fraction in for the base. Instead of rising to the right, now it's falling to the right. The other thing is 1/2 is a larger number than 1/4. It looks like the smaller the fraction, the steeper the graph. So let's look at y equals 2 to the negative x and y equals 1/2 to the x. If I take y, or 2 to the negative x, and I kick that 2 downstairs, I get 1 over 2 to the x. Well, 1 over 2 to the x is the same as 1/2 to the x. And the reason is 1 to the x over 2 to the x is the same thing as just 1 over 2 to the x. So these are equivalent, all three of these expressions. So if I graph y equals this, I should get the same thing as if I graph y equals this. So anytime you have a negative x, it's going to fall from left to right, just like we noticed when we had a fractional base. I want you to notice that the rigid transformations that we've already studied apply when we're doing exponential functions. If you add or subtract something to the x before you do your function, that is going to be a left-right shift. So this would be a shift to the left of 1 unit. The gray graph here is my standard unit of my graph, and this black one has been shifted to the left. Over here, we talked about if you do your function first and then add or subtract, it's an up-down shift. So again, the gray graph is my parent graph, the black graph is my shifted graph. We know that if we negate a function, that reflects it over the x-axis, so this is no surprise. And if we negate our x before we do our function, then it's a reflection over the y-axis. Now there's a special number called e that's often used in banking and in science when we talk about decay and growth. And the number e is kind of like the number pi. It's a special number. It's a non-ending, non-repeating decimal. It's an irrational number. E is approximately 2.7. This number is called the natural base. So we can take a look at the exponential function using e as the base, and it's called the natural exponential function. All right, here's the graph of y equals e to the x. It doesn't look really any different than the other graphs we were looking at, and it shouldn't because e is about 2.7. So it's kind of like graphing y equals 2.7 to the x. We would expect it to rise left to right. And it's going to be a little bit steeper than y equals like 2 to the x. If you're told to find values for a natural exponential function, there is a button on your calculator for e. So you could type the button e, then the caret, and then the number. Or there's also a function, if you hit second e to the x, that automatically puts e in your base, and then the number that follows is your exponent, and then hit enter. Here's a place where you might see an exponential function. It's often used in banking. This is a formula for figuring compound interest. The A stands for the amount that you have accumulated in your account after T years. So T stands for the number of years. P is the principal that you start with. R is the annual interest rate as a decimal. And N is the number of times per year that the interest is compounded. So if it's compounded quarterly, then N would be 4 because it would be compounded then 4 times per year. Different financial institutions do it differently. So let's just look at a quick example. If a bank gives you 6% interest and it's compounded quarterly, then you would put a 4 in here for N. T is your time, so this number here would be your time. So this number is T, this number is N, this is your rate as a decimal, and this is the principal that you've invested. If you calculate that all together, this is the amount of money that you would have after 10 years if you started with $4,000 invested at 6% with compounded interest quarterly.